Hey there, welcome to the video. My name is Gavin and today we're going to be doing a physics tutorial on Faraday's law. So our goal is to learn what Faraday's law means and how to use it to determine the induced electromotive force. Before we do that though, we first have to take a couple steps back and understand what exactly is electromagnetic induction. Up until this point, we've only looked at circuits that use batteries to produce a current. Batteries use chemicals to create a voltage that drives the electrons through the circuit. This is great for powering things like our phones and other gadgets, but what if we wanted to power something bigger? A battery would take up too much space. So is there a way to produce a current without batteries? We've already discussed how if you pass a current through a coil, it generates a magnetic field around it, like a bar magnet. This means that an electric current can generate a magnetic field. So this begs the question, if an electric current can produce a magnetic field, could a magnetic field produce an electric current? If so, we've managed to answer our question about how we could produce current without using a battery inside of our circuit. This question about whether a magnetic field could produce an electric current was the driving question behind Michael Faraday's experiments that led to the discovery of the Faraday law. So what exactly was Michael Faraday's experiment? For his experiment, Michael Faraday took a ring and had that act as a circuit, and to that he attached a device. This device had the capability of measuring electric current that was running through the circuit. It is this by detecting which way the electrons are flowing, and as such, it can detect whether electrons are flowing in one direction or the other direction. This device, which is called a galvanometer, is something that was used to measure the current in the device, in the circuit. So for the next part of his experiment, Faraday took a magnet and set it next to this circuit. He observed that there was no current that was running through the galvanometer, despite there being magnetic fields in close proximity to that circuit. From this, he was able to determine that despite the magnetic fields being near this circuit, the magnetic fields themselves, just by themselves, would not produce an electric current. However, as he was kind of maybe taking apart his experiment, he realized that there was he realized a little movement in the galvanometer. And what he soon figured out as he looked back at it and he started moving the magnet around was that as he moved the magnet around this circuit, there was indeed a current produced. Without a battery, showing that it was produced by the magnetic field. So this showed that when the strength of the magnetic field was shifted or altered or changed, we could produce an electric current. So now we have to talk a little bit about electromagnetic induction so we can understand what exactly it is. So it is simply the process by which a current can be induced to flow due to a change in the strength of a magnetic field. So now that we've discussed electromagnetic induction, there are really two keys to understand this, or two laws that really break apart this concept and help us determine things mathematically. The first of these keys, the first key is going to be Faraday's law. The second of these keys is going to be Lenz's law. And for, the focus of our video today, we're going to be mainly focusing on Faraday's law. So, Faraday's law was founded by Michael Faraday in the 19th century. This law just simply recites the rate of change of a magnetic field, or magnetic flux, through a loop, which is going to be delta flux divided by delta t, is going to be equal to the magnitude of electromotive force in the loop, which is just shown by the epsilon. So the electromotive force, or EMF, many people don't know what that is, but it simply refers to the potential difference across the unloaded loop of a circuit, or a coil. Or in other words, basically the EMF is equivalent to voltage. Both of them use voltage as their main units, and they're just measuring the potential, in a circuit. So that's basically it. Another concept many people aren't familiar with is electric flux. It's not something that comes intuitively to people. But basically, electric flux is the rate of flow of the electric field through a given area. We depict that by showing, the symbol for flux is equal to B, which is the magnetic strength, times A, which would just be the area of the coil that magnetic force is working on. So using the concepts that we just learned, let's work through this practice problem. So, a small 10 millimeter diameter permanent magnet produces a field of 100 milliteslas. The field rapidly drops away with distance and is negligible more than 1 millimeter from the surface. If the magnet moves at a speed of 1 meter per second through a 100 turn coil of length 1 millimeter and diameter just large. So to start working through this problem, we want to start by writing down the equation for Faraday's law. So that's going to be the EMF is equal to the number of turns divided by the change of flux divided by the change in time. After that, we're going to write down the equation for change in flux, which is just going to be the flux 2 minus flux 1. After that, we're going to want to determine, what is flux 1. Because in this problem, we can assume that as the magnet moves away from the coil, there's going to be zero flux, because the magnetic field is not going to be affecting the coil at all. After that, we're going to determine flux 2. Flux 2 is going to be equal to the equation that we discussed earlier. It's going to be equal to the strength of the magnetic field, which is 100 milliteslas, times the area of that coil, which we can get from the small diameter. So we can determine the area by doing 10 millimeters times 10 to the negative third meters divided by 2 to get the radius, and we will get 5 times 10 to the negative third meters. After that, we're going to plug it into the equation for the surface area of a circle, which is going to be pi times 5 times 10 to the negative third meters squared. Now that we have that value figured out, we can move on to figuring out how we can determine delta t, or the change in time. So to determine delta t, we're going to want to look at the speed at which the magnet is moving through the coil and how large the coil is. So we can assume that because the magnet is moving at 1 meter per second through a length of 1 millimeter, we can get the change in time by multiplying the distance traveled by the inverse of the speed. And from that, we get 1 times 10 to the negative third second. So one of the things we didn't write down on the last page was what our N value was. So if you remember, N is just the number of turns that we have in our coil. So that is going to be equal to 100 turns. So now let's take our equation and let's start substituting in everything so we can just plug our values in. So the EMF is going to be equal to the number of turns divided by the flux 2 minus flux 1, all that divided by the change in time. After that, we can break that down even more, so flux is going to be equal to the number of turns, and then our flux 2 is going to be equal to the magnetic strength times the area minus flux 1 divided by the change in time. Now we can start plugging in our values. So our EMF is going to be equal to, let's plug in our value for number of turns, which is going to be 100. Forgot the negative there, plug that in. Then we're going to multiply that by, let's plug in our values for our magnetic strength. So it's going to be 100 times 10 to the negative third Teslas. Then we're going to multiply that by our area. And our area we have is going to be pi times 5 times 10 to the negative third meters, and then all of that squared. Alright, now that we have that, then we're going to do that minus our flux 1, and then our flux 1 is going to be 0 Teslas. Alright, from there we can plug in our delta, our change in time, which is going to be 1 times 10 to the negative third seconds. And when we plug that in and calculate that out, we get our EMF is approximately equal to 0.78 volts. Well, thank you so much for watching this video, and I hope that you've learned a lot, and I'll catch you next time. Okay, now that we have all those values figured out, let's move them over to a different sheet that we can continue to work on.